Welcome back to Material and Energy Balances. In Chapter 8, we learned how to deal with a change in pressure, temperature, and phase of matter as it relates to the change in enthalpy of a process stream or a system. Here I'll also point out that enthalpy can also change if the composition changes, and we refer to that as heat of mixing, but we skipped how to calculate it. So I won't be covering that in this semester, but you're welcome to look into that if that's something you're interested in. If you've ever been curious about in chemistry lab, for example, when you mix H2SO4 with water, you may have noticed that the temperature changes of that mixture, and that's owing to the heat of mixing, or the heat of solution is another word for it. In today's class, we're going to start chapter 9, and that will cover the enthalpy change due to a change in the identity of the components themselves. We call that a heat of reaction. The heat of reaction comes about because there's energy that is required to break chemical bonds and energy that gets released when new chemical bonds are formed. Just as a quick example, let's take the combustion of methane, CH4, on the left, to form carbon dioxide and water. So I've got a methane molecule drawn and two oxygen molecules, which is the stoichiometric quantity. And we are going to form a mole of carbon dioxide and 2 moles of water. What has to have happened in order for this reaction to proceed? I must have broken all these CH bonds. So that's just a cartoon of me breaking those bonds. I also had to have broken the oxygen double bond, but I also had to have formed these carbon-oxygen double bonds and these oxygen-hydrogen bonds. This is what I was just referring to. That breaking of chemical bonds requires energy in order to do that, and forming of chemical bonds releases that energy. We call the net release of energy, so that is the energy released minus the energy required, that is called the heat of reaction. So delta HR is the symbol for the heat of reaction. And it's important to note that that is defined for a stoichiometric quantity of reactants reacting at a certain temperature and pressure to form products at that same temperature and pressure. So just like the enthalpy of vaporization was a function of temperature and pressure, the heat of reaction will be a function of temperature and pressure as well. Let's talk about a couple of notes about delta HR. The first one is that at low or moderate pressures, we can assume that the heat of reaction is a function of temperature only. Remember, this is mathematical notation that whenever you see the parentheses like this, the variables inside the parentheses are going to be the independent variables. So this means that the heat of reaction is a function of temperature only, not a function of pressure, and this is usually a good assumption. So there's parallels that you can draw here to the enthalpy of vaporization. Remember how, or just enthalpy in general, most times we say that the effect of pressure is small relative to the effect of temperature. The second note is that the reaction stoichiometry is going to matter now. So it matters how you define or how you write your reaction stoichiometry. So here I've written two seemingly consistent or identical chemical reactions for the combustion of methane. The only difference is in the second equation, second chemical reaction, I've multiplied all stoichiometric coefficients by 2, which shouldn't change anything. However, the heat of reaction, let's call this delta HR1 and this delta HR2. These heats of reaction are not going to be equal to one another. So it's important to note that the heat of reaction is defined for the reaction as written. So as I've written it here, this heat of reaction is going to be equal to twice the heat of reaction for reaction 1. And that reflects the fact that I now have twice as many reactants. So related to that, you can say that the heat of reaction is defined per 1 mole of methane reacting, or per 2 moles of oxygen reacting, or per 1 mole of CO2 formed, or 2 moles of H2O formed. And you can write that in terms of any one of the reactants or the products. Third note, and similarly, the state of matter matters. So again, I've written the combustion reaction for methane in 2 different forms. The first form produces water as a vapor product, and the second form produces liquid water as the product. So here, once again, if I define what the heat of reactions here are as delta H1 and delta HR1 and delta HR2, these are not going to be equal. So the fact that I have liquid water produced as the product is going to change the heat of reaction relative to if I had water vapor formed as the product. The fourth note refers to some terminology that we'll see soon, that the standard heat of reaction, so the symbol for that is delta HR with a little degree sign up next to it, is at a reference T and P, and that reference temperature and pressure is at 25 C in 1 atmosphere. Once again, you have to be aware of the fact that if your reaction is occurring at a temperature other than these standard conditions, then the actual value of the heat of reaction is not going to be equal to the standard heat of reaction. Let's get into a practice problem next. This problem says the standard heat of combustion of liquid N-octane to form carbon dioxide and liquid water at 25 C in 1 atmosphere is delta H hat C standard is minus 5,471 kilojoules per mole. Briefly explain what that means. Your explanation may take the form of when blank, yada yada. So the first thing to do here is to write the full balanced form of that chemical reaction. Here is that chemical reaction, which has been balanced, which again is important because stoichiometry matters. And I've also input all the phases of matter into this chemical reaction as well, because that matters as well. Here I'm assuming that that octane is a liquid, which I can guess by looking at what the boiling point temperature is and noticing that the boiling point is above typical room conditions. Actually, no, it says liquid N-octane right in the problem statement, so I don't even have to assume that. It also says liquid water as well, so it probably should say both of those things. Oxygen is a gas unless it's extremely, extremely cold. Same thing for carbon dioxide. That's going to be in the gas phase. So what does that mean? When 1 mole of liquid C8H18 and 25 halves moles of O2 gas react to form 8 moles of gaseous carbon dioxide and 9 moles of liquid water, the change in enthalpy is minus 5,471 kilojoules. Is this reaction exothermic or endothermic at 25 C? So the answer to that is looking at whether or not the heat of reaction is positive or negative. And here I have a negative heat of combustion. So how I think about it is that the final energy must be less than the initial energy. And that's the only way that I can have a negative. So the reaction is going to be exothermic. That's because it's giving off energy. So if you look at what the heat of reaction is, if you take the system to be the chemical species, then if those lose energy, then that must mean that the surroundings have gained that energy. So you would have to cool the reactor to keep the temperature constant. And what would the temperature do if the reactor ran adiabatically? It would increase. What can you infer about the energy required to break the molecular bonds of the reactants and that released when the product bonds form? So energy required to break is going to be less than, greater than, or equal. It is going to be less than the energy released when products form. All right, and that's one of the reasons why a combustion reaction is so effective, is because it gives off energy. It releases energy when those product molecules form. If 25 moles of liquid octane is consumed and the reactants and products are all at 25 C, estimate the required rate of heat input or output in kilowatts, assuming that Q dot is equal to delta H dot for the process. What have you also assumed about the reactor process in your calculation? You don't have to assume that it equals 1 atmosphere. So for this part, I have to share an equation that I did not derive. The derivation is in the textbook if you're interested. This is equation 9.1-4b that says delta H can be equal to the extent of reaction. So this is going to come back again. So chapter 4 stuff now again showing up in chapter 9 times the heat of reaction at T naught and P naught. So if 25 moles per second of liquid octane is consumed, then I can say that the extent of that reaction is 25. So in this example, I'd have 25 times the standard heat of combustion or heat of reaction, 5,471 kilojoules per mole. So that calculation is minus 1.37 times 10 to the fifth kilowatts. And that is going to be a heat output in kilowatts. So you could say that the heat output is 1.37 times 10 to the fifth. And I've also assumed that the reactor pressure is not necessarily 1 atmosphere, but I'm assuming that 1 atmosphere is, or that whatever pressure it is, doesn't have to be 1 atmosphere, is low or moderate, such that the heat of reaction is not a function of pressure, only temperature. Okay, part D says the standard heat of combustion of N-octane vapor is delta HC is 5528 kilojoules per mole. What is the physical significance of the 57 kilojoules per mole difference between this and the heat of combustion and the one given previously? That significance is that the enthalpy of vaporization is 57 kilojoules per mole for N-octane at 25 C and 1 atmosphere. And the final part E says the value that is given in part D applies to N-octane vapor at 25 C and 1 atmosphere, yet the normal boiling point of N-octane is 125.5 degrees C. Can N-octane exist as a vapor at 25 C and at a total pressure of 1 atmosphere? Explain. This is something that we've talked about in chapter 6, that oftentimes water exists as a vapor at temperatures below its boiling point as well. So there's humidity in the air all around us. This is the same type of concept. And the answer to the question of can N-octane exist as a vapor at 25 C and a total pressure of 1 atmosphere? And explaining my answer is yes, if it is in a mixture. Remember, it's the partial pressure that matters here. And again, same thing for water vapor. So that'll do it for this video. In the next video, I'll discuss Hess's law.